Hi everybody, we're finally on chapter 13 and we are now going to start talking about correlation. What is correlation? I think it's a statistic that most of you are familiar with. Most of you have heard about this statistic. Let's define it. First of all, it is different from the other statistics that we've talked about so far in that all of the tests that we've examined, so z-tests, t-tests, ANOVAs, all of those tests that we've looked at previously have compared group means. So at the heart of those tests, it's asked the question, do these groups differ statistically? Are the means different from one another statistically? So those are what I call difference tests. Pearson's correlation is different in that it's not comparing group means. It's not a difference test, it's a relationship test. So what it's really doing is examining the degree of a relationship between two variables. So as you can see here, it's defined as a test that measures the degree of linear relationships between two interval or ratio level variables. So if these two variables are said to be related, they're said to be correlated, okay? So let's take a really generic, really easy correlation to understand. It's alcohol consumption and blood alcohol level, right? So the more alcohol a person consumes, the more their blood alcohol level is going to rise. So for any individual, you can measure two variables. So for each case, you're going to measure two variables, and you may or may not see these variables relate to one another. In this example, you should see that the more alcohol a person consumes, the more their blood alcohol content will rise. And if you measure this over a number of cases, statistically, you're going to see a correlation between these variables. Now, what's really important to understand is that correlation is not causation. Hopefully you have heard this before, but if you have not, ingrain this in your head, okay? Correlation does not ever imply that there is a causative relationship between your variables. It doesn't mean that there isn't necessarily. It simply means that with a correlational design and a correlational statistical test, you can't assume that a causative relationship exists. So the reason is that in a correlational research design, what you're doing is simply measuring variables as they naturally exist, okay? You're measuring how much a person is drinking in alcohol, and then you're measuring how much their blood alcohol content is, all right? In that research design, you're not manipulating anything per se. You don't have a lot of experimental control. So there could be a lot of other reasons why a person's blood alcohol content may be increasing. So we can't say that there's a causative relationship. It makes sense in that example, but we can't say necessarily there's a causative relationship, okay? So there might be other reasons why a change in X might be leading to a change in Y. So we're going to get to this in just a moment, but just kind of keep that in your mind for now. The most important thing being right now is that in a correlational design, we're not manipulating things, and we're not doing random assignment like we are in an experiment, okay? So what you're also going to find in correlation is that the variables that we are measuring are often referred to as variables X and Y. So for each case, we're going to measure two things, X and Y. And oftentimes, if we think there's an order to that relationship, we might call X the predictor and Y the outcome. So before we do any analysis in correlation, we always take our data and we present them on what's called a scatter plot. All right, this gives you a visual analysis of a relationship, if one exists, And here is an example of the number of community hospitals and the number of deaths per year, okay? So for various states, they measured how many hospitals there were, and at each hospital, they measured how many deaths were reported. And so you can see down here is Delaware, very few hospitals, very few deaths that year. And over here we have New York, a lot of community hospitals and a lot of deaths. Now this is a great example of relationship between two variables, the number of hospitals and the number of deaths per year. Clearly we see visually this relationship. We're going to talk about it in a little bit, how this is a positive relationship, but how this relationship is not causative, okay? If we were to put Texarkana on here, and let's say Texarkana got a huge grant and we decided that we were going to build, you know, let's say 300 hospitals, would that mean that we're going to have 180,000 deaths? No. Why? Because simply having more hospitals does not cause more deaths. The reason why New York has more deaths is because New York is more populated. All right, New York being more populated needs more hospitals, and because of that, it's going to have more deaths. So this positive correlation exists because of this third variable that's out there, and that's population. So that's why, one reason why we can't always say correlation equals causation. There's this third variable, which is population, which is leading these two variables to be related to one another. So let's look at this relationship here. These are just randomly generated X and Y variables. If we were just to do this up here, you see no visualization of any relationship. On here, we have foot size and IQ, two variables that shouldn't be related whatsoever, and we see a big blob. We can't make any sort of trend line on here, and we should see that there really is a zero correlation. So what would a perfect relationship look like? Well, a perfect relationship would be a straight line. For every incremental increase or any incremental change in one variable, you should see an equal incremental change in another variable. So if we were to take temperature and measure it two ways, Fahrenheit and Celsius, and then plot those two temperatures, we will see an exact straight line. That's a perfect relationship. So what about the strength of a relationship? Scatter plots also provide you with that information. So here's a perfect relationship, right? This is the strongest relationship you can have. Well, the tighter that line is, the stronger the relationship is. So what we have in the second figure here is, you know, compact scatter plot, but not as strong as the line here. And then as it becomes looser and looser, you see the relationship becoming weaker and weaker. And as we'll get into later, the value, the statistical value of that relationship is also going to indicate that it's a weaker relationship as well. So the way that we're going to quantify correlational relationships is by what's called a correlation coefficient, okay? That is our test statistic that we're going to eventually calculate. And it's a number that's going to summarize in a single number, because a statistic is also always a single number, the strength of a relationship between two variables. So in the next video, we're going to talk about that number, and we're going to talk about the information that we can garner from it. So this is the first video and probably a few that I'm going to post. If you've got questions about this, as always, don't hesitate to contact me at asikorsky@tamit.edu. Take care.